Welcome. On this lesson, we'll be discussing the multiplication and division of complex numbers. Well, let's start by stating two complex numbers. So here we have two different complex numbers, because remember that this is how we can represent complex numbers. So r cosine plus I of sine, this is how we can represent a complex number. But I want to use the subscript 1 to indicate that this is a complex number, and I'm going to represent the subscript of 2 to represent that this represents a second complex number. So we have two complex numbers. And now let's observe some of let's observe this conclusion here. So we are going to define the first complex number as 3 cosine of 45 plus I sine of 45. And we're going to define the second complex numbers as 2 cosine of 30 plus I sine of 30. And now take a look at this conclusion here. We're saying if we were to multiply these two complex numbers, then my result would have been 6 cosine of 75 plus I sine of 75. So here I'm already giving the conclusion. So now the question is, what happened? Can we write down a formula that we can use to multiply complex numbers? So what exactly happened when I multiply these two complex numbers? Because if I get this complex number and I multiply it by the second complex number, this is my result. Well, let's see what happened when we multiply complex numbers. Well, the first thing that you might have noticed is that if we take a look at the value of r, if I multiply them, it gets me 6. So perhaps when I'm multiplying complex numbers, I'm really just multiplying the values of r. But now, what exactly happens to the degrees? Because notice that we're still talking about cosine and sine, but notice that I started with 45, then I multiply a complex number that uses 30, and my result is 75. So what can I do to 45 and 30 for me to obtain 75? But notice that we just add those degrees. And if we simplify this, 3 times 2, that's 6. And 45 plus 30, that is 75. And 45 plus 30, that is still 75. So this is how we were able to obtain that conclusion. So notice that when we multiply complex numbers, really what just happens is the values of r's are going to get multiplied, and the actual arguments, or the actual degree of measurement inside the cosine and sines, they're just going to be added. So if we just want to write down a formula, we can say that if I'm multiplying two complex numbers, what essentially happens is I'm going to multiply the module of the first times the module of the second. And then when it comes to the arguments, I'm just going to be adding their arguments. So this is a formula that we can use to show what happens when we multiply complex numbers written in complex form. So this is the multiplication. When we multiply complex numbers, all we got to do, we got to multiply the r's, and we just got to add the degrees. But what can we do, or how does division work? So still, same idea. We have defined a complex number in this form, and we have defined a second complex number in here. So what happens when you divide complex numbers instead of multiplying complex numbers? Well, instead of multiplying the values of r, we're going to be dividing them. So 0, 1, remember that 0, 1 is being defined as r1 times cosine of theta 1 plus I sine of theta 1. So if I'm going to be dividing complex numbers, I need to divide their values of r. And when I was multiplying them, I was adding their degrees. But now, when we are dividing complex numbers, we will going to be subtracting the value of their modules. Huge difference. Multiplication, we multiply the values of r and we add their degrees. For division, we divide the values of r and we subtract their degrees. But very important, it's always going to be the way that we're going to be subtracting them, it's always going to be the degree of the top minus the degree of the bottom. Because notice at first I'm doing the degree of the z1 and then I'm subtracting the degree of z2. So this is how we're going to be defining multiplication and division of complex numbers. Very important two formulas to remember. So now let's actually confirm or verify that these results are true. And for that, we're going to be doing a smaller group activity. So we're going to be using the definition of the product and quotient of complex numbers, complete the following. So what exactly do we want to do? First, we want to write down the trigonometric form of complex numbers, which this is yesterday's lesson. So let's do that first. Let's take a look at A. Again, let me just make myself a little more space here. Let's take a look at A. Oops. All right. We have two complex numbers that are being multiplied. So first, let me try to rewrite those complex numbers in trigonometric form, because notice that what we want to do, we want to verify this is actually true. So your complex numbers need to be written in complex forms, in trigonometric form here. So let's concentrate on my first complex number. So 2 minus 2i. Let's try to rewrite this number in its trigonometric form. Well, first, let's identify where it's its location. For the location is at positive 2, negative 2, so it's about right here. So I know that this point is going to be on my fourth quadrant. So let's actually try to write down this complex number using trigonometric form. For the first thing that I want to find out is the value of r. And according to yesterday's discussion, the value of r, it is the real square, so the real part, which is 2 squared, plus the imaginary square. So r, it's equivalent to 4 plus 4, which is the square root of 8. Which we can still simplify as just 2 square roots of 2. Okay, so we know r. So what else do we need in order to write down our complex number in trigonometric form? Well, we need the value of the argument, or the value of theta. But I know that if I take the tangent of that angle, that's still going to be equivalent of b over a. Remember that this is something that we discussed in our previous lesson. But here my b has a value of negative 2, and here my a has a value of 1. So now we know that the tangent of 1 is equal to negative 2 over 2, which is just negative 1. So now we want to find out angles which I can use that will give me, that if I would evaluate on tangent, it gets me a value of negative 1. And that will be, so now I know that angle 1, that will be negative pi over 4. Why is it negative pi over 4? Well, let's go back to our unit circle. But we want to find out the tangent. We want to find out an angle that if I plug it into tangent, it gets me negative 1. But recall that tangent, we can only use values between the first and the fourth quadrant. So therefore, the only possible value that can give me negative 1, it will be exactly 7 pi over 4, which is just equivalent to negative pi over 4. Because this is just from here to here, that's 45 degrees. 45 degrees is pi over 4, so therefore from here to here, it is 45 degrees, but on the negative direction, so negative pi over 4. So that's how we obtain this. But what is the actual argument? What is the actual argument? Because we know that from here to here, that is negative pi over 4. But recall that that's not what we use to write down. That's not what we use to write down our complex form. What we need our complex form is the whole argument, which is this green degree that we do have here. But notice that the actual argument is going to be the full circle, so 2 pi minus pi over 4, which if we simplify this, this is just going to be equivalent to 7 pi over 4. So 2 pi, it's about here, and if I take away pi over 4, which is this negative pi over 4, that is equivalent to just 7 pi over 4. So now that we have this, now we can say, look, the complex number 2 minus 2i, that's equivalent to r, which in this case is 2 square root of 2, times the cosine of 7 pi over 4 plus I sine of 7 pi over 4. All right, so we did all this work just to show the actual, well, let me see if I can just move this, because we're not going to be discussing example B. All right, so we're back. All I did, I just moved down our result just down here, so we can just have more space to work on. So all we did, we just rewrote these initial number, complex number, into its strict form. So let's try to do the same for my second number, 1 plus I. So let me actually just separate this. So let's try to rewrite that number, 1 plus I, in its complex form. Well, again, let's start by just defining its location. My location is 1 real, 1 imaginary, which is here. That's the first quadrant, which is great. So now let's actually find the value of r, where r is the real square, which is 1 square plus the imaginary. But notice that if this is I, there's always an imaginary in front of it, imaginary 1 in front of it. So that's 1 square. So now r is equivalent to just the square root of 2. So now that we know what r is, we have to find the actual angle of measurement, or our theta. So, but recall again, the tangent of theta 1 is equivalent to b over a. So if we put it all together, b is 1, a is 1. So now we're looking for an angle that if I take the tangent of it, is equivalent to 1. But notice that we have that at 45 degrees. We have that at 45 degrees because tangent is sine over cosine. So sine divided by cosine, anything divided by itself, it's always 1. So now I know that my theta 1 is equivalent to pi over 4. Do we have to do any changes? Well, I mean, this is what we just found out. We just discussed that this is pi over 4 degrees. Do we have to create any changes, or do we have to modify anything just like we did previously? Well, no, because here my theta 1 is the same as my theta, just like we discussed in our previous lesson. So now that I have this, I can say that the complex number 1 plus I, this is equivalent to the value of r, which we found it to be a square root of 2, times the cosine of my theta, which is pi over 4, plus I sine pi over 4. And notice that we have not done anything new so far, because all that we have done is we have just done an extra example from yesterday's lesson. So now that I know that I can rewrite those complex numbers in this complex form, let's actually show that the formulas that we just explained previously, let's actually show that this formula works out. How can we show that it works out? Well, first of all, Let's multiply it, like if it was just a regular distribution. So if it was a regular distribution problem, what would be the outcome? Well, 2 times 1, that's 2. That's 2i. That's negative 2i. And that would be negative 2i squared. So then now it just becomes 2. They cancel out. So negative 2. I squared is negative 1. So now this just becomes 2 plus 2, which is just 4. So I know that if I were to just distribute them, I should obtain a value of 4. So now we should have still got the same result if we were to just multiply them using the formula that we just discussed previously. So let me use a different color. So now what would have happened if I would have done the same problem? 2 minus 2i, 1 plus I. But now I use the equation or the formula that we just discussed a couple seconds ago. Well, my formula says that I know that this complex number is being defined this way, and I know that my second complex number is being defined this way. So if I want to multiply them using the formula we just discussed, what I have to do, I have to multiply the values of r. So 2 square root of 2 times the square root of 2. And when it comes to the angles, I have to add them up. So in this case, it will be 7 pi over 4 plus pi over 4 plus I sine 7 pi over 4 plus pi over 4. And if we do everything correctly, we know that we should have gotten a result of 4. Well, let's see if that is true. So now we got 2 square root of 2 times square root of 2. Well, that is 2 times the cosine 7 pi over 4 plus 1 pi over 4. That's 8 pi over 4 plus I sine, and again, 8 pi over 4. Now this becomes 4 times the cosine. Oops, sorry. But now, let me actually backtrack myself a little bit here, because we know what's, well, let me simplify this. Shouldn't be making any shortcuts here. Well, 8 pi divided by 4, that's equal to just 2 pi plus I sine 8 pi divided by 4. 8 divided by 4 is 2, so this is 2 pi. So this is the result that we would have gotten, but this does not look anything. This expression right here does not look anything like 4. But notice that we can still evaluate these expressions, because now this becomes 4 times. What is the cosine of 2 pi? Well, 2 pi, it's a full circle, so the cosine of 2 pi is just 1. So now this becomes 1 plus I, the sine of 2 pi. But what is 2 pi? Again, 2 pi is right here, and the sine value is just 0. So now it becomes times 0. So now it becomes 4 plus 1, any imaginary times 0, which is just 0. And now this becomes 4 times 1, which is just 4. So notice that our formula works out fine, because I knew that if I would have just if I would have just done the problem that we have done previously, a couple months ago, then we would have seen that my result is just 4. And we have just shown that if I do the same problem, but now if I use the formulas that we just discussed a couple seconds ago, I still got the same result. So we have just kind of confirmed that this formula works out. Again, a very good side note is that if we want to use this formula, your complex numbers need to be written in complex form. And now you might be asking yourself this question: why do I have to do all this extra work right here? Like, this is just not necessary. All this, because I could have just gotten the same result if I would have just distributed them. Well, for this example, yes. But there might be times where you want to multiply more than two complex numbers. Well, there might be times where we want to multiply 4 or 10 complex numbers. So, do you really want to distribute 10 times? You're going to get a big number, and the chances are that there are going to be some signs that are just floating around there, and it's just going to be too much. So right now we're practicing with just two numbers, and you will see on the next lesson how we can expand this to whenever we want to multiply to 10 or even more complex numbers at the same time. So hopefully this was helpful, and I'll see you in the next lesson.